We are now in E of exercise 3, where we want to find an approximation of the ruin probability for large U. Now, according to Theorem 215, we have that if the ladder heights are sub-exponential, then for the initial capital tending towards infinity, the ruin probability will be asymptotically equivalent to this expression that we have over here, where mu denotes the mean value of a claim size. And in this case, since y is log normally distributed with parameters m and sigma squared, that mean value is e to the m plus sigma squared halves. So we will use this approximation to plug in our values and write up an approximation of the ruin probability for large U. By Theorem 215, we have that the ruin probability for large U is equal to lambda divided by C minus lambda e to the m plus sigma squared halves multiplied by the integral from U to infinity of the survival distribution of the claim sizes. And that's what we have spent A, B, C, and D trying to figure out. So we have an expression from up here, which we may plug in. So we just have e to the m plus sigma squared halves multiplied by the distribution function in a standard normal distribution. Minus u multiplied by the standard normal distribution function in m minus log u divided by sigma. Okay, so we could say that this is an approximation and that's enough. We could stop here, or we can take it just one step further and try to write up something nice instead of these two distribution functions. There is a formula which tells us that for x tending to minus infinity, the standard normal distribution function is equivalent to e to the minus x squared divided by 2 divided by x scaled by 1 divided by square root 2 pi with a minus in the front. There we go. Now we can show this result by L'Hopital. We can also just choose to use this result. I would say just use the result. But if you wish to show it, then it is possible to show by showing that if you take the standard normal distribution function and you divide by this entire expression, then you want to show that this entire thing goes towards 0 for x going towards minus infinity. And you show that this entire thing goes, did I say 0? You want to show that this ratio goes towards 1 for x going towards minus infinity. And the way you show that is by taking the derivative of both these expressions and using L'Hôpital. And after you do that, you may plug in the expressions inside each of these. And then you get, well, the reason why we want to use this expression is because when u goes towards infinity, minus log u goes towards minus infinity, and then this entire argument goes towards minus infinity. And exactly here we have a result that tells us what this entire argument is asymptotically equivalent to, as what this entire function is asymptotically equivalent to as the argument goes towards minus infinity. I'm actually kind of rambling here, but you can see that what you have to do now is you have to plug in the values m plus sigma squared minus log u divided by sigma in the two places of x here, and then try and see if things cancel out. I think when we get to this point, the calculations are already so messy that you won't really learn too much from doing them. So what I can say now is just plug in the values, and then if you move things around a little bit, you should arrive at the following solution, which is lambda multiplied by sigma to the third multiplied by e to the minus log u squared plus m squared divided by 2 sigma squared. And then you multiply by u to the m divided by sigma squared plus 1. And that entire thing is then divided by square root 2 pi multiplied by c minus lambda e to the m plus sigma squared halves multiplied by log u squared. If you don't want to go through those calculations, that's also completely fine. Just have this formula for your formula book, that this holds when x goes towards minus infinity, because that is a useful, a very useful result.